Sorry.
Good afternoon. Many thanks for your time. So this is an update on segment routing. So in October 2012, at a Cisco-hosted conference with 80 operators, I made a presentation on a proposal of segment routing. And there was a lot of interest in the room. We formed a lead operator group. This was October 2012. In March 2013, so 1 year from now, here at the MPLS World Congress, I made the first public presentation on segment routing together with working code of the first use case that we had defined it with the lead operator group. At the same time, we released 2 IETF drafts, and immediately Alcatel and Ericsson joined the project. In July 2013, supporting the IETF process and the standardization, seeking to have interoperability because my key target is the operators, and it was a key requirement, a key commitment that I made initially, that we would seek interoperability and standardization and bring other vendors on the table. We released 8 IETF drafts, and at that time, Juniper joined all the protocol extension draft. In November 2013, at MPLS ISOCORE, I made the first public presentation on topology-independent LFA, that is an automated IGP-based fast reroute for link and node failure in any topology, together with working code and together with Stéphane and Bruno from Orange, one of the operators that have been working with us tightly on this technology definition. The code was working at that time. We could demo it. 12 IETF drafts were available at the IETF to support the standardization process. The Spring Working Group to standardize segment routing was formed. Today, it is the 1-year anniversary of the first public presentation. There are 15 IETF drafts. All the major vendors are participating to this, clearly sponsored by the operator take-up that is massive. So really thanking the operators to work with us to define their requirements, their use case, because that's the target for the project. Today, in this presentation, I'm going to detail yet another use case. And when I do it, I have working code, I can demo it, and we're building this as a product. We focus to resolving problems, building product, deploying it. In July 2014, in November of 2014, there'll yet be other use cases because the original lead operator group that worked with us a year ago, 18 months ago, has drastically expanded. And as we have looked at segment routing, more and more use cases surface on the table. And that's great because all of these use cases only require very few protocol extension in ISIS, OSPF, and PSEP. That's a sign that we're doing something very good. Few extensions, many use cases, many deployments, left and right. So a very quick summary of the different use cases that you can test on Cisco devices at this time. The list on the left is going to FCS next quarter, so you can deploy it starting next quarter. And the list on the right is in beta, and you can ask for a proof of concept. Specifically, I attract your attention to topology-independent LFA together with the interworking with LDP. I think it's a massive use case. There's a lot of interest to it, and the way to deployment is clear. The second massive use case that I see is the one that I'm going to first publicly describe today. It's the segment routing traffic engineering use case. So what about centralized traffic engineering? Well, a centralized TE controller maintains an up-to-date network model. It continuously retrieves the policies on the network, the topology, and the traffic matrix. The centralized controller that we are building can be used in 3 flavors. It can be used as a planning mode, as an on-demand tactical traffic engineering solution, or it can be used in autopilot mode. In planning mode, it's a human being, a planner, that works on a quarterly basis to redesign, add capacity in his network. This was carried in original product. In tactical mode, it's someone in the NOC, in the operation, that reacts to a sudden change in the network in terms of an outage or a traffic surge, and basically use the central optimization to find a solution to rebalance the traffic in order to meet the SLA objective. In the autopilot mode, it's the same process but automated without the human being that acknowledges before the solution is programmed into the network. In the rest of this presentation, I'm going to detail the middle option, the tactical, human-driven, operational traffic engineering based on centralized optimization. So I start with my controller that retrieves the information from the network, and at the current time, this is my topology, and I have a very well view of my demand matrix. Here, I just illustrate a subset of the traffic, the subset going to node 4. If there is an outage, the controller, because he's directly connected to the network, is immediately informed. And because the controller has an up-to-date network model, he immediately reroutes in his network model all the demands in the model. And so he sees that due to this outage, the IGP shortest path in the new topology for the purple demand, the demand that goes from 2 to 4, is now going to be rerouted via the link 3-4. And so, because he maintains all the SLA objectives, he deduced that this IGP reconvergence is going to push too much traffic on the link 3-4 with respect to the SLA target for that link. And so immediately the controller is going to compute for a solution based on segment routing traffic engineering. And this solution here is basically to look at the orange flow, the flow going from 1 to 4. Naturally, it would follow the IGP shortest path. And this would put traffic on the link 3-4, but we know it is going to be congested. So the optimization algorithm finds a way to reroute a minimum of the traffic using the minimum number of tunnels, using the minimum number of segments to build that tunnel. And here, the solution is to reroute only the demand 1 to 4 via a traffic engineering tunnel segment routing base that goes via loose hop 5. This is beautiful, because a segment routing-based traffic engineering tunnel is built with a list of segments that are prefix segments. Each prefix segment is given by the IGP, and each prefix segment is ECMP aware. So it is really helping a lot the controller to have a balanced solution between smart, intelligent, thin, distributed control plane and just what is needed from an optimization computation and from a programming to have something very swift, reactive, and scalable. In this mode, in this flavor, the controller is going to inform the operator, you have an outage, here is the solution I could propose to you, do you want to push it into the network? If the human being says yes, then the controller sends, use again this very little PSEP extension that has been defined at the ATF, and the controller sent that PSEP message to router number 1, and it says, well, router number 1, I'd like you to build a segment routing traffic engineering tunnel. Destination is 4. Loose hop only 1 at 5. And I want you to put demand 1 to 4 on it. So very elegant, because it's only one state, quickly injected at router number 1. So swift reaction based on centralized optimization. We know that centralized optimization is more optimum and is more predictable than distributed traffic engineering as done by RSVPT or PNNI in the last 15 years. And I don't have to say it, it's very clear, and Mr. Husel from Google, that leads the network and data center architecture, has very nice presentation showing all these flows in the RSVPT traffic engineering problem. So here, we're trying to address a requirement by saying, yes, we want optimization centrally. It is going to be more optimum. It's going to be more predictable. But we want to find a way to make it agile and scalable. And so segment routing gives you that distributed infrastructure to help that centralized optimization. So this is in demo. If you want to have a demo, if I would have the time, I would love to give you the demo. But please contact your account team, and it will be great to walk you through the demo. More important, and that's my key objective for me today, I'd like you to look at these questions. The questions you should ask is, how fast can this be computed? How many tunnels are required? How many segments are required per tunnel? How fast does the overall process? These are the questions. And, well, my answer is to say, judge on your data. We're building the product, and we are at a stage where the product is available. We have used it on the data set, the real data set of a few operators, and I can say that for them it has been extremely interesting, extremely eye-opening, because it's a new alternative. My goal today is not to convince you that this is the solution for everybody of you. And my goal is not to say that this is a replacement for RSVPT. My goal here is to say, I work with operators. They gave obvious requirement for a better traffic engineering solution. I am trying to build an alternative, and I only want it to be judged on real data. And that's why just judge it yourself with your own real data. And so the tool is, at this stage, good enough that we can actually produce this analysis for you. I'm very fortunate that one of the operators agreed to use their data today. So it's a real data set. It's a very large network. It's the network that today is using 50,000 RSVPT tunnels to do the traffic engineering solution. I'm going to show you two charts that would be available to you if you want to see what it means for your network. This first chart is showing that if I use the topology of that operator and the traffic that they have to support, and if I don't do a traffic engineering solution, I just use ISIS, and I simulate all the possible outages that can occur in the network. There are thousands of links. I only show the 72 worst-case link failures where the outage would be the worst. I clearly see with the red line that building this network with only ISIS is not possible. Because for 72 link failures, I have massive congestion. I have two solutions. Either I pay more and I put more capacity, and here I need 50% more CapEx investment in the network to make it work with ISIS, or I don't pay, but I have a traffic engineering solution. So the gain of doing a traffic engineering solution is kind of 50% of the CapEx, so it's significant. We want to find a traffic engineering solution that is applicable to this problem. What you see with the green curve is the result of applying centralized-based traffic engineering, centralized-based optimization with segment routing, traffic engineering, tunnel placement. We see that we solve all of the problems. We are always under the 100% bar for the 1,000 link in the network, as well for the 72 worst case. You see that there are 6 issues that I cannot solve today with segment routing, traffic engineering. So I saved the question. I already gave the answer. For these 6 out of 1,000, 3 of them are unsolvable. If this link fails, there's no longer enough capacity in the network to support the traffic matrix. It is not a traffic engineering problem. It is a capacity planning problem. You need to add capacity to solve that problem. So it means that out of 1,000 links, I have only 3 links that cause problem, and I admit it's early in my productization process. I have still many ideas. The algorithm is not complete, but I'm very confident that we will solve them. So we'll see next year, and hopefully I'll have documented and released many more studies like this. But I am confident, and I'm optimistic. The second chart is very interesting. It's the blue curve. It is now showing the number of tunnels that I need to use for this. This data set is using today 50,000 RSVPT tunnels in the deploy network. This is well described by Mr. Hussel's presentation as being non-predictable, as being non-optimum, and it's well known in the industry to be very complex to operate. It is well known that such a size, if there is a link failure, it may take 15 minutes to converge. So there are many issues, and I'm working on real problem statements from operators. Here, in the analysis that we see, in this data set, and it only is valid for this data set, to solve the problem, you cannot see the number of tunnels I need to inject with segment routing. It's completely flat on the bottom of the curve, the light blue curve, because for each of these link failures, I need 1 tunnel, or 2 tunnels, or 3 tunnels, never more than 10 or 15 tunnels. And the beauty is just like the intuition I had given 18 months ago at the Cisco conference. You do not need many segments to reroute the traffic away from the link where you have the congestion. That's the intuition that the human being use every day to decide their route on the highways to go from one place to other. The networks are built by human beings. They follow human-based infrastructure. The same property will be seen. That's great to have intuition. With data, you can see whether it's true or not. So I think this is eye-opening. This is extremely interesting. We see that we can solve it with global optimization, it's more predictable, it's more optimum, but we are also generating a solution with 1,000 times less tunnel, which means that from a scalability and from an agility viewpoint, that is much better. And obviously, the centralized controller is the great point to have the API into the application to request the application-driven admission of flows into the network. So that's where the SDN linkage is for segment routing. Before doing the segment routing project, I was running the IP optical optimization project at Cisco, and you have this IEEE paper that we wrote together with colleagues from Deutsche Telekom and Telefonica. Always, I run the project operator-based, real problem-focused, and I really invite you to read that paper, because the tool that I am building, the technology that I'm building for segment routing, is doing a seamless integration of what I described before, segment routing-based traffic engineering with global optimization and the IP optical optimization, again, from a centralized viewpoint. So for me, it's one single tool that I want to deliver to the operators. Conclusion, for us, we believe that segment routing, as many in the industry, is very important for the IP MPLS infrastructure, because it's a balance between distribution and centralization, and it's a great point to interact between the network and the application. The distribution, we are building a very slim but powerful and intelligent control plane that distributes the segments and that makes sure that these segments are always protected for link and node failure in any topology. That's the scope for distributed control plane. Then on the centralization viewpoint, we're building a centralized controller that does centralized optimization and that deals with the application. If there is any need to react and rebalance the traffic in the network, it's done in a swift way by injecting segment routing-based traffic engineering tunnel at the entry point to the network. My point is not to convince you that this is the right thing for you. My point is to try to work with you, to do the data analysis, to show what it means for you, and you make your own conclusion. We have the simulators to do topology-independent LFA analysis for your network. We have the optimization here for segment routing-based traffic engineering and centralized optimization. I really invite you to judge on your data. Many thanks. And I'd like to thank really the operators to have worked tremendously on this project, because it's really their work defining what are their problems and their requirements.
Thank you very much, Clarence. So thank you very much for this passionate presentation, and also because we have some time for questions. So please, in the audience, if anyone wants to ask a question to Clarence. Okay, someone? Oh, okay. Didn't expect.
Clarence, thanks for showing the simulation results. Actually, I did see a quantitative analysis, but I didn't see a qualitative analysis. I mean, how long does it take for a centralized controller to update a 50,000 LSP full mesh, i.e. you have to manipulate, just by doing the maths in my head, 200 routers with 250 destinations each. And I would just be curious, how long does it take the centralized controller to update that massive amount of forwarding state using remote IPCs?
Great, thanks. Is it possible to show the slide? Because that's a great question, but it's exactly a great question because it helps me to, again, add something. I am really thinking out of the box. So I am not doing traffic engineering the way it has been done for the last 15 years. So I am not solving that problem. I am solving another problem. I'm saying, look, the way I build an IP network is that I want it to be simple and fast and predictable. So I want my traffic to ride shortest path all the way. And so I build the optimization product to leverage IGP, ISIS-OSPF forwarding as often as possible. And the controller, what it does, it just, whenever there is an outage or there is a surge that is exceeding a threshold, it recomputes and it determines, well, what do I need to do? And the number of tunnels that I need to inject, do I have a laser? It's here. So for example, if I have I'll do it here. So if link number 40, let's say 22 fails here, if I don't have segment routing based, so if I just have ISIS, my network will go to 150% link utilization. Congestion will occur. I'll have a problem from an SLA viewpoint. I do the optimization, and I find out that I can bring the network back to that state, so I avoid congestion. But what do I need to do with my solution? I need to inject this amount of tunnels. This is what I said. I need to inject 2 or 3 tunnels. You cannot see it here because it's too flat on the curve. I don't want to operate full mesh of 50,000 tunnels. I want to write IGP shortest path as often as possible.
Clarence, I think actually it's very interesting from the following point of view. What you seem to be saying is that if you use centralized controller and if you want to squeeze as much as possible out of IGP for the purpose of traffic engineering, then in fact you'll need very few explicitly routed tunnels, period.
That's my point.
Well, and if that is your point, then I think RSVPT would be just perfect for that purpose, because if you have only a few tunnels, RSVPT state cannot be an issue.
Look, you are totally right. You are totally right. But then I'm asking you the question is that from an operation viewpoint, RSVP, the only point of it is to build an explicit path and do bandwidth admission control along the path. If you have optimization centrally, the bandwidth admission control is redundant, it's useless. It's something you have in your network for nothing. Second, the signaling is to do explicit route. Well, you have it with segment routing with only a state that you inject on the head end. So it's more elegant. Agree that you can use all tools to also do it, and there's no issue with it. But that's not an argument to not say that go for the slim behavior, the just elegant behavior.
Well, the only thing I can answer to this is that elegance is on eye of a beholder.
No, but you are a vendor, and I think you are emotionally linked to RSVP, so you'd like it to be used often. I don't care for me. I will support this with RSVPT tunnel head end, and I will support this with segment routing traffic engineering tunnel. I look at my operators. I do what they want.
My name is Victor Liu, Huawei Technologies. I have done some technical TE in OffNet technologies about 10 years ago. So is there any general performance study between your SR-based technical TE and RSVPT? It's kind of like same as Jakob's.
Yeah. So Hannes asked another question, how fast? So let me try to do the maths. How fast can the controller detect the outage? A second. How fast can it compute? I have the results under NDA with the operators. In the chart, there's a chart that I remove. It's how fast we compute. The current state of the product is not optimized, but that's very, very fast. So I'm very proud of that data, but I prefer not to say it. It's too early in the productization. So I compute in real time, and then I find a number of tunnels that I need to push. 3 tunnels. Let's say I need to push 10 tunnels. So it's 100 milliseconds per tunnel, so maybe a second. So we're going to be, for me, I would be very happy to be even under 5 minutes, because I know that the same scale is 15 minutes in the industry today.
Clarence, interesting presentation. Just a couple of questions. How do we address multicast? If I have an MLDP-based implementation, how would that sort of fit into the scheme of segment routing?
I don't see where the question is coming, just for the icon.
I don't see neither.
Okay, great. Look, my position on this is very clear since the beginning. I lead the project, so I run it like this at Cisco. I do not fix unneeded problems. I don't see any problem with multicast. My use case, my requirements from my operators are unicast driven. I am solving unicast problem. I need to have something much more agile, much more flexible, much more scalable to fit in an SDN environment, and that's what we're working on. And so from a multicast viewpoint, I am not aware of any scalability problems. So if one has MLDP for multicast today, if one has RSVP for, or PIM for multicast today, what's the point of solving reinventing a solution where there's no problem. I'm not in that business.
The follow-up to that is, and this is a follow-up question, that I think one of the important things that you mentioned about segment routing is that it removes the state information, from the core. It makes it light. But I think when we talk about it in the context of RSVP only, we are forgetting the fact that there are large-scale LDP implementations, running VPLS or point-to-point pseudo-wires and so on. So just trying to figure out why the RSVP is being looked at as...
I think it's the same vendor. You are taking it, you look at it technologically, like a protocol X against Y. I don't look at it, for me, I like RSVP. And if in the use case of that operator, it's the best solution, for me, it's the best solution. It's just that I have many other use cases where RSVP is not the best solution, and so we are investing to give people the choice. If X has a need for a certain solution, he will use segment routing. If Y has a need for a solution based on RSVP, he will deploy with RSVP. There's no one is better than the other. There's a variety of requirements.
Okay, thank you. Thanks.
And I wanted to add something on multicast, is that a bit like the last quote from George, when you see things happening that the universities start to think, people start to think, I am not driving a multicast solution, but I am aware that some people get to think, and maybe some people are going to propose something one day. That may happen, but that's healthy, because it's healthy for people to propose. If they find, the key is to ask, will they find operators that have true requirements? This I don't know, and we'll see. But at this time, I don't see any issue with multicast.
Thank you very much, Clarence. Thank you.